Good evening, ladies and gentlemen. The appointed hour having arrived. My name is Jeff Badnock, and on behalf of the University of Montana Alumni Association and the Alumni Association Community Lecture Series Committee, I'd like to welcome you to the second in our series of lectures on Shoot the Moon. Our format is that we'll have a lecture given by a University of Montana faculty member or emeritus. And then following the presentation, we will have an opportunity for questions from the audience. I would ask you right now first to silence your phones, in case you're going to be one of those people. And when the microphones come around for question time, because we are being recorded by MCAT, I will remind you to speak directly into the microphone. Don't hold it down here. Shoot your voice right into it so that we can collect your questions, so the audience that sees the taping of this is able to hear what it is you're asking. This year, we are beginning each lecture with a poem about the moon. And one other thing. When you came in, there's music playing. I don't know how many of you hear it or can identify the songs, but each and every song that's played in the intro while you walk in is related to the moon. Tonight's poem is by a Chinese poet, and although I took a year of Chinese at the university 30 years ago. I'm not going to read it to you in Chinese. I'm going to read it to you in English. It's by a Chinese poet whose name is Li Po. And this is a poem about Li Po, his jug of wine, the moon, and the shadow that comes from the moon. Drinking alone under the moon. A jug of wine amidst the flowers, drinking alone with no friend near. Raising my cup, I beckon the bright moon. My shadow included, we're a party of three. Although the moon's unused to drinking, and the shadow only apes my every move for the moment, I'll just take them as they are, enjoying spring when spring is here. Reeling shadow, swaying moon, attend my dance and song. Still sober, we rejoice together. Drunk, each takes his leave. To seal forever such unfettered friendship, let's rendezvous beyond the Milky Way. And now it is my great pleasure to introduce tonight's lecturer, Dr. Steve Running.
Let's see, testing 1, 2, 3. Testing 1, 2, 3. Want it up higher? Testing 1, 2, 3. You'd think I could have a poem or something. Not very original on this part. Is this about right? Okay. We rolling? Okay. So when I saw the theme of this lecture series about going to the moon, and then they wanted me to talk about Earth science. And I thought, how's this going to work? And it's actually, I hope I can weave through the story of NASA and Earth science in this next hour, and give you I could just give kind of a history of NASA Earth science, and they had a 60th anniversary last year, and on their websites they have some really cool animations of all sorts of stuff, as you can imagine. But then I thought, I can do that early history, but then I actually lived and participated in most of the Earth science history of NASA. And so why don't I tell them my story, because it all happened while I was here also. And so this is going to be partly the NASA Earth science history and partly what your tax dollars were paying for me to do up in the science complex for 40 years. And so you'll get a little bit of both. And let's get going. I had not known that the first images from space were done in 1946. I'm sure this was a film with a film camera, and what they used to do is they'd take pictures and then parachute the film out of some canister down to the ground, and I'll bet that's the only way they could do that 1946 one. The first digital image was 1959, and of course we can't even tell what it is. and of course you recognize this was with an early digital camera. And think of that, 1959, and we didn't start getting serious about commercial digital cameras till the 90s. So this was the start, and that incidentally is a cloud deck over the Pacific. I found out by reading the caption, not that I could tell. And so here's where NASA Earth satellites started, right about 1960. The Weather Watcher, the Tyros satellite. On the left, Nimbus 5, the next generation satellite in 1964 was launched. And the important thing I want to point out for kind of my theme of the night is initial NASA Earth science. The only thing they really cared about was weather. They didn't care about any land science at all. And so all through the 60s, all through the 70s, the progression of satellite development for Earth was primarily about the weather. Now we all know, and other speakers will tell, the absolutely glorious history of manned space flight through the 60s and the 70s. And certainly going to the moon, many trips and landings on the moon through the 1970s. I mean, those really were the glory days of NASA. And at NASA headquarters, they still think back that way. Them was the good old days. When I went to Cape Canaveral a couple of years ago, it was very clear to me that they had severe nostalgia for the old days, and particularly the space shuttle launches. And right now, the only thing Cape Canaveral is particularly being used for is to launch beer up to the space station for the astronauts. I saw one of the canisters that they fill full of beer and then send them up. And so Cape Canaveral can't wait for manned spaceflight to start again. And it got me thinking that the first couple of decades of NASA was all about manned spaceflight, and the little bit that wasn't was weather. Was some of the very earliest weather forecasting. Now the one exception to that was the Landsat series of satellites, and probably a fair number of you have seen or maybe even worked with Landsat satellites over the years. Started in 1972, and the important, and there's been a whole development. We're up to Landsat 8 right now. We're building Landsat 9 as we speak, and so this is an ongoing series. The important thing is Landsat was basically like a telescope looking down, and so you saw a small piece of the Earth. You never had a global image. We didn't successfully process, and I say we, the grand earth science community, certainly not my lab. The first time I saw a full global image based on Landsat was only about 5 or 6 years ago. And so Landsat, for all of its history virtually, was high-resolution regional scale science and land management. It was not global science because the data sets were just too big. The swath was way too small. And so it was never meant to be a global data set. The global scale Earth science started with Tyros. You see it, I better get practice. Yeah, launched. This is right about the time I got here. September 1979, I started my position here. This was a weather satellite. And so it initially was not designed to do any kind of land science. It certainly wasn't designed to look at vegetation or ecosystems in any way. But luckily, a couple of curious graduate students started playing with the Tyros AVHRR data set. It was actually a graduate student at Colorado State University, and he was there at the exact same time I was at Colorado State University. We didn't know each other, and the worst thing of all is I never took a remote sensing course while I was there. And if it would have helped in my future if I would have known. But at the time, I was a very detailed tree physiologist. And so he did the first looking of weather satellite data and whether and if he could discern any kind of useful patterns on vegetation from this weather satellite. And that, starting around 1980, was our first global look. And we're going to look at that a little bit more. Now I go into some kind of large-scale, what should I say, science history. And, of course, it starts with the Keeling curve of atmospheric CO2 measured at Mauna Loa. And there in the left-hand corner is Dave Keeling riding up the Snowball chairlift with me years ago. This has been called the most important geophysical data set of the century. And yet he used to struggle to get funding. And so it doesn't matter how good a science you're doing, funding's never going to be easy, is the only conclusion I could come to from that. But what's important for our discussion here is he started this in 1957. The data set was just, let's see here, okay. We were just about to here around 1980. The issue of global change and global warming was just barely starting to be defined and discussed in the science community. Not in the public yet, even in the science community. In 1980, there was not any broad, large-scale study or discussion of global change. But this data set was enough impetus that there were starting to be small discussions. And what I find very ironic is I owe my career to Ronald Reagan. Because it turns out right as Reagan came to office in 1981, and he was getting to know what different agencies did, and when he found out what NASA did in Earth science, what they were doing at the time is using Landsat data to try to figure out the Russian wheat yield. So it was basically agricultural commodity gaming. And Reagan told the NASA administrator, I want NASA to do big science. If I want to know about the Russian wheat yield, I'll call up the Department of Agriculture. Go have NASA do big science. And literally, that was when NASA decided, well, we got to figure out what's the big issues in Earth science. Right about the time the Keeling curve was starting to say, it sure looks like the global carbon cycle is getting out of whack. The CO2 in the atmosphere has been going up for a couple of decades straight. And so NASA called around to a number of ecologists at the time and started talking to them. And of course, they didn't call me. I was an assistant professor teaching dendrology. But what they did do, to my eternal good fortune, is call my old major professor. And he was a pure tree physiologist, and he could not think to global scales, and he knew he couldn't. So he actually turned down NASA in invitations to these early think tanks. But he said, you know, you ought to try calling my old student Steve Running. He's ready for some big thinking. And so in 1981, I'd been here on campus 2 years doing some, early tree physiology sort of work. I was invited to the panel that wrote this thing, Land-Related Global Habitability Science Issues, dated July of 1983. And so this, as an assistant professor, was my entree into NASA Earth science, and this was NASA's first time of thinking about Earth science in any big way because of the Keeling curve and because Reagan pushed NASA to go find some big science questions to go after. And so I am really not being smart when I say that Reagan made my career. And so in that document, I sketched out this concept where you could gather up daily meteorological data from the satellites. You could measure a number of attributes of the ecosystem with the satellite, and then you could calculate photosynthesis of the whole world. And so basically I sketched out this concept. It had never been done before, and I'd never done it before, but I thought I could do it. And so I put it into this global habitability document and said, here's the kind of thing that NASA can start doing in Earth science, is not just using the satellite data as an aerial picture. Like Landsat was basically, you just looked at a picture and you could see Flathead Lake and Missoula and the Bitterroots. This was then a step towards quantifying attributes of ecosystem processes, and particularly the carbon cycle. NASA had never seen anything like it before. I hadn't either, actually, when I think about it. And so this was really just me lobbing in an idea that I thought might work. Well, that landed me on the team that designed the key sensor for the mission, and this was this moderate resolution imaging spectrometer. And I'm on the science team for MODIS to this day. And so this started in 1984, and it's 2019. So we designed sensors, but this time we had some this time we were specifically trying to design this sensor to look at ecosystems and look at vegetation, which had not been done ever before by these global satellites. So rather than this being a weather satellite, this was going to be designed for ecosystem research at the global scale right from the outset. And I still remember sitting through some absolutely brain-melting lectures on optics theory, of how you get, you bring the reflectance in through the front end optics, and then it bounces around in mirrors and goes through spectral gratings, and I'm just going, I'm a forester, come on. So, but it really was, as I look back on it, an unbelievable experience. This was the real rocket science crowd designing rockets. So just about the time we'd had a couple of years where we wrote a few documents conceptualizing large-scale global ecology issues, global habitability. We'd started designing what would be the right kind of satellites to do the sort of work that we envisioned. We had flow charts like the thing before that had been conceptualized. Right about that time, the Challenger accident happened. And NASA, of course, politically took an absolute nosedive. And I think almost everybody in this audience was alive for the Challenger accident. And so, I mean, you can read this. Following that accident, there was a task force at NASA headed by Sally Ride trying to answer the question, what can NASA do to get back on its feet, to gain back the public trust, gain back the political support, and continue to do big things. And there were 4 recommended leadership initiatives, but as you see, the mission to planet Earth was the #1 highest priority objective they put forward. And so here was our chance at the big time. After NASA had spent decades in manned space flight and going to the moon and launching the space shuttle, and here finally it was time for us to, in effect, eat at the grown-ups table. And so 3 years later, George H.W. Bush authorized and Congress funded the mission to planet Earth. And so that was right about 1990. And so at that point, I'd basically been thinking about all this for 8 or 9 years. And for I don't know if there's any graduate students in here, this is an illustration that big science does not happen fast. And so here after 9 years, we're just getting started. But we finally were a significant part of NASA. So to give a look to this day, this is a few years old, but the NASA overall budget breakdown hasn't changed a whole lot. You'll notice that space operations about $4 billion, including the space station is the biggest one. Space exploration, another $4 billion. Aeronautics, space technology. There's Earth science. Out of approximately a $20 billion overall agency budget, NASA Earth Science has sat at around 10% for a couple of decades now. So 90% of the agency is doing other stuff. And we're kind of over in the corner trying to get respect. We are the biggest of the science divisions by a fair bit. But I always have to be reminded that NASA still ultimately is more after human space flight and going to Mars and things like that than it is Earth science. We're only 10% of the show in the agency to this day. So, kind of a bureaucratic summary slide of what the Earth Science Division does at this point. When I retired here in summer of 2017, I also retired. I was chairing the Earth Science Advisory Committee at the time, and had been for 4 years, I think it was. So I was actually able to hang around the top floor of NASA for a good number of years and see it, I guess you'd say, from the inside, and get that sense of, I'd have to call it tension. It really was subtle, but real tension between Earth science, the other space exploration science, but the big elephant always was human spaceflight, and is to this day. All right, now let me return to what we decided to do back in 1990. So I remember the mission to planet Earth was started in 1990. They had a big call for proposals of scientists worldwide that could propose to do whatever their specialty was on these platforms. And there's the biggest proposal competition in NASA Earth science history, before or since. And I was the only one that proposed doing anything of higher order ecosystem carbon cycle, namely photosynthesis and transpiration. The only one in the whole world. And I couldn't believe it at the time, and I, to this day, still can't believe it, but I had no competition. Of course, NASA could have decided it wasn't worth figuring out global photosynthesis, but if they decided they wanted to, they had to come to me. And so I was selected for the science team, and we started building this AM1, as it was called, the Terra Platform. I think it's useful for us to get a little bit of a look at the scale of these things. So you can see a stepladder down here, and so you can get the idea. This thing's a couple of 1,000 pounds, about the size of a minibus, and this was about the largest thing we could launch at the time. So we were not only money limited, but weight limited. The rule of thumb of the time is it took about $10,000 to launch each pound into space, into orbit. Didn't matter whether it was a hunk of lead or a spectrometer, each pound cost you something like that. So every pound counted. And so this was our AM1 that became the Terra Platform. And here, my sensor was the biggest one on the very end. And off it went to launch. A few of you might have been around. President Denison was president at the time, and a lot of us went to the launch at Vandenberg. A lot more met up in my lab to watch the launch live. Turned out, as launches go, the first one was scrubbed with, I think it was 9 seconds left. And one of the things I learned there, you learn all sorts of things hanging around with this crowd, is at T-minus 60 seconds, all human intervention ceases. It's all up to computers after that. No human could think fast enough to have blinking lights of some warnings and register what to do fast enough. So at T-minus 60 seconds with any launch, it all goes over to computers. When the launch scrubbed, they didn't know why. There's been a hold on launch, and then we're all just sitting there, just melting with stress, and they say, basically, we'll get back to you later. And it wasn't a couple hours before they found out that it was just one parameter on horizontal wind speed that had gone over limits, and so the computer scrubbed the launch. But 2 days later, we did way better, and off it went. So we got this into orbit right at the end of the last century, and so basically January of 2000 is when we started. And I want to make another point that I find interesting, maybe you will, about how strategy of satellites has changed since then. So this satellite had something like, well, we can go back, 9 different sensors on it. It cost a couple of $1 billion for sure. And at the time, we thought that was essential to have these all together for a variety of reasons, and efficiency of providing power supply and onboard computing and data downlinking and all that kind of stuff. Today, the strategy is really turned around. Nowadays we have what this is called the Atrain. This is a sequence of satellites. This is the one after Terra, so this was another big one. But all of these, I realize you don't know the names of any of this stuff. The only thing I want you to notice is look at they're only about a minute or two apart, or 3. Back in 1990, as we planned the mission, there's no way that we could steer satellites that accurately. And so we had to put them all up on one big platform. And if we would have lost that one on launch, I would have been back to teaching tree physiology. But nowadays, they can steer the satellites so precisely. It's just unbelievable. They can these are all smaller satellites that have really only one primary sensor and one primary raw data stream. And they can launch them anytime they want and then get them up there and line them up in a train. And that way, you're not risking everything on one launch. And you can also bring satellites in, and as one becomes obsolete, you can pull it out. And so this is a lot safer, and and we find that it's a lot more efficient overall. Nowadays, just to go back here, I think 4 of these sensors are now dead, or they're not meeting spec. That doesn't quite mean they're dead. That's not fair. I think a couple of them are dead and a couple of them are out of specification. But nowadays, we launch smaller satellites and we line them up there, and then when they're done, we bring them down and shoot them into the ocean. And so this is the sort of thing that's up there now. And when I think that when I started, there was Landsat and there was Tyros. And it's just unbelievable. Over the, I guess, 40 years that I've been in NASA Earth science, I'm not about to go through sensor by sensor and tell you what they all do. I couldn't even do it if I tried. I'm supposed to know, but I forget stuff nowadays. But there's just dozens and dozens of our satellites, and of course other countries also. Now there's a ton of Earth science going on from all these satellites, and this is kind of one of my favorites. I'm sure all of you have seen these. I wanted to point this one out because it was totally an accident also. Kind of like looking at vegetation from a weather satellite back in 1980. We used to, the computer capacity was low enough. We used to, on the night side of the orbit, you just dump the data because you didn't have processing capacity. And this one guy at NOAA, Chris Elvidge, one time, who knows what he was doing late at night, but he thought, I'm going to just take a look at one of those backside images. And that's where the night light started. This is one of the most highly used data sets in all of NASA Earth science nowadays. It totally started by accident. It actually tells you all sorts of things about socioeconomics and energy use and stuff like that, more so than regular Earth science. And it's incredibly valuable and incredibly interesting, and it was all a fluke. It was never designed. Our newest satellite has a channel specifically tuned to optimize this data set now. And so the newest data is way better than the old ones. One of the things that NASA's always found interesting to look at are fires, and so this is a Landsat image from 1998 of some of our fires. This is another image. You all recognize our home region, and after the fires of 2000 and all these burn scars all around. This is my favorite one. This is from the Space Shuttle, And this is what those smoke plumes that we're down underneath standing here gasping, and this is what it looks like from above. Now I could, and I get maybe I should ask, how many of you have heard one of my climate talks over the years? Okay, so maybe a quarter of you. I'm not going to talk about climate hardly at all, and tonight for once. This is for me kind of a joy to be able to talk about my own earth science. So I talk about things like monitoring Arctic sea ice and the climate talks. We're not going to talk about that. I talk about things like sea level rise and how sea level is going up 3.4 millimeters a year. And we have laser altimetry satellites that measure it with very high precision. And the streets of Miami are starting to look like this on a normal king high tide. But I ain't going to talk about that either. Now I'm going to talk about what my science at University of Montana put into this mission to Planet Earth. And so starting with when I left Oregon State, and when I think back, I realize that when you're working in things like tree physiology, you don't ever imagine that any journalist will ever want to talk to you. You certainly don't imagine that you'd ever be invited to give public talks, because tree physiology just isn't something that people normally want to hear much about. And so I was trained to try to understand transpiration of trees, and it was only as I made this transition to global scale ecology that you start becoming policy relevant. And so this is what my PhD research looked like, sitting up in a tower with this thing called a null balance barometer measuring transpiration. And this was basically what got me into NASA, though, is I was one of the very first ecologists to give a try at computer modeling. And so I did this first little model of water going through a tree. We could put your Christmas tree in this model and see how it does in 1975. But the act of first translating ecology into quantitative measurements, which ecologists didn't do much of back in the 70s, and then the systems analysis thinking that I learned to do this kind of modeling was what allowed me to then come up with the kind of concept for how we could do photosynthesis globally from a satellite. And so I had, at the time, was working on this model, which I sat and ran this thousands of times over there in the science complex, that evaluates how carbon, water, nitrogen, and energy interact in a forest ecosystem. And so this I started working on in around 1980. So this was what I was doing with my own research at the time. And it turned out that that was the kind of thought process that was going to be helpful. Now, at this point, right about that time, 1983, the knowledge of global scales, NPP, net primary production, which is a technical word basically for plant growth. So this was global plant growth as best we knew it in 1983 when I started thinking about this from my thinking that looked more like this. And so I thought, this shouldn't be very hard to beat this. This was some geographers that were doing some very simple correlations of plant growth with annual precipitation. And that works about halfway. But certainly with no direct global measurement. And so this is when the first satellite measure of vegetation index was being developed. So I'd mentioned this a little bit earlier. This guy down here, Jim Tucker, invented this thing called the Normalized Difference Vegetation Index. And all that is a spectral index that's tuned to greenness. It in effect amplifies the greenness signal in the satellite record. And this was a big enough deal that he got the cover of Science in 1985. We had never seen an entire continent ever before, except in Rand McNally maps. And I mean, you think back to then, we hadn't got back away from the Earth far enough to have ever seen the whole Earth in these early 1980s. So he had this vegetation index that he had developed, and I had my ecosystem model of photosynthesis, respiration, and transpiration, and I put them together. And this is an analysis I did for Missoula. You see the year 1984, and this is what the satellite saw, and this is what my model saw. So I saw a couple of things. First, that the satellite basically defined the growing season pretty darn well. But as we learned particularly, it gets confused by snow on the ground, and it certainly gets confused by summer water stress. But based on this, I figured, all right, this is sufficiently interesting that this is worth figuring out how to do a more advanced model. And so this is that same figure back from before, but now with some context. That you see, I'd been working with ecosystem model basically at the tree level for about 10 years, but now I had to think through how that might do globally, and so this was this same diagram from before that to me seemed pretty straightforward. And so off I went. I wrote a proposal in 1989 that was funded in 1990. Made lots of headlines here at the time. It was the biggest grant in the history of the university system, of the whole Montana university system. So it got great notoriety back around 1990. And this is what my lab looked like at the time. And everybody remember the IBM XT with 8-inch floppy disk drives? I think my hard disk was 20 megabytes, and I just paid the moon to get an upgrade from 10 megabytes. I mean, you have pictures on your phone that are 5 megabytes each. And but this was the state of the art of the time. And one of the things that's been very clear to me over the last 30 years is we could have never done the global science, even with the global satellites, if we hadn't had the computer revolution along with it. In fact, I remember the very first time I was at Johnson Space Center and they showed me a Landsat image. And so this would have been 1982, I think. The screen, I could watch the screen refresh. It was so slow. The scan lines refreshed one by one. You don't even know that's how a screen refreshes, I'll bet, because it just pops the whole thing up nowadays. But back then, it took about 10 minutes for one screen refresh of one Landsat scene in 1982. And so none of this science that we talk about could have ever made it if we hadn't had the computer revolution along with the satellite revolution. So what I worked through is this scaling logic, as they like to talk about it, where you start here with plot level understanding, then you work with these flex towers, and then you go up and use the same logic from the plot level science, but to the global scale. And so I did. And with my very first PhD student, Ramakrishnan Namani, who last year was anointed a distinguished alumni of this place, if you happen to remember. And so this was part of his PhD dissertation. Now you folks can recognize this landscape. I don't know if you can recognize, but this was the first spatial simulation ever done. And it was published to the first color image in the journal Ecology. So this was absolutely groundbreaking in global science at the time. This is more like what we do now. And this is the way, with our satellite-based analysis, we look at effectively the same landscape, and you can see a whole lot more detail, a whole lot more precision than before, but it still started with those fundamental principles. We even did some doubled CO2 climate change test, and so this was on that. You can always use Flathead Lake for a geographic reference there. So we doubled CO2 in our model, ran the model to equilibrium, and it sure looked like to us that Montana forests would grow faster because their growing season would be longer, except for the low elevation forest will run out of water. The high elevation forest won't, but the low elevation forests will do well until they run out of water. And I'd have to say, almost 30 years later, the fundamentals that we wrote in this paper are still basically true. This is still what we are expecting. The one thing that this model did not do was in any way try to simulate disturbance like wildfire. And so that's the big additional dimension that we couldn't handle at the time that we certainly know now is quite real for us. All right, so I'd done a regional model there, and now we had to get this global somehow. So the first thing we did was had done a global, just pure simulation of photosynthesis, and so this is the whole world, not mapped in geographic space, it's mapped in climate space. So on this dimension is temperature, so I mean, basically this is the hot, dry desert down here because it's hot and it's dry, and going up the y-axis is water availability. And so you can go from hot, dry to the Amazon is up here, hot, wet. Missoula is about right in the middle of everything. But this was my attempt to try to understand the ecosystem constraints of the whole world. And so this was a valuable first step. I won't crawl through the details, but what that allowed us to do, and of course at this time I had 6 or 8 PhD students that were hot on all of these details with me, so we had quite a lab here going. And what we ended up with was this evaluation where any place on Earth we could give you a basic partitioning of control of the ecosystem by water, by temperature, and by radiation. And so anywhere in this, this was really just a climate analysis. And so obviously in the very far north, it's totally temperature limited and light limited. Right now, you know, up in Barrow, Alaska, they haven't seen the sun for 3 months, and it's just now starting to come back. In like manner, with this analysis, we could evaluate the deserts as very warm, very sunny, but no water, and basically everything in between. And so we put all this together to what I'll just call, for simplicity, global effective growing season. And you see that basically just some of the simple principles of tree physiology I used, and I actually spent more time evaluating the climatology than I did the ecology. And so this was the way that I was able to take some simple principles of how plants operate to a global scale. And we compute 110 million cells per day with this data set. And actually, we've now gone below 1 kilometer, so it's now bigger than that. At any rate, so this was our very first global photosynthesis from MODIS. It had never been done anywhere on Earth, and so we did it here. And this is what it looks kind of ugly, actually. It's probably not even correct either. But by 2003, we had a big paper in Science where we used this algorithm with the older satellite and the newer algorithm, and we're able to project that in especially high latitudes, we were seeing increasing rates of photosynthesis. Then a few years later, 2010, we had a second paper in Science where we evaluated that there were sufficient drought impacts in dry areas that the net plant growth of the planet appeared to be going down a little bit. And so this was really the first attempt to see if we could even tell where the direction of global scale plant growth was going. Now this is what we have. Oh, no, it has to work. Oh, man. I even practiced with this. Okay, there. And so this is what our data set looks like now, and shows the big green wave in the spring. Now, you understand that we have a 5-foot diameter digital globe here at U of M. Does everybody know that? It's over in the foyer of this School of Education. It's been broken for a year, and we're on the way to getting it fixed, and this data set is on that digital globe, along with 100 other data sets. The Montana Natural History Center has a digital globe also, about a 2-footer. And these data sets on an actual sphere are really spectacular to see. And so this is the kind of data set that we now generate every 8 days. This is going on to this day. And so it's come a long ways from those very primitive fixed images that we started from in 1983. And that was only about 20 years from a standing start to be able to be doing this 20 years later. Now, an important part of this, and I'm not going to dwell on it other than to let you know that it's real, is all this satellite-based algorithms and theory, it could be way off. And so luckily we had a validation system that emerged during the time of development of our satellite, and it's called FluxNet, or globally Ameriflux. And what this is a set of towers all over the world that measure carbon dioxide, water vapor, and all the meteorology nonstop. It's all automated. The map of where these are, this gives you a look. They're all over the world. We first, some friends and I started imagining this in 1995 at a retreat in Italy, and nowadays there's 517 active towers. What this gives me at every point of those towers is this place where I can specifically validate the calculation my satellite algorithm makes of carbon dioxide flux and evapotranspiration measured by the tower against my satellite calculation. If it hadn't been for this, I would have very little confidence in my results. They'd be nice pictures, but I wouldn't actually have much confidence in them. So now we can look with the old satellite connected to the new satellite this is 20, 30 years of global plant production and ask the question, well, is it going up or is it going down? And as I said, our paper in 2003, we thought it was going up, and then our paper in 2010, we thought it was going down. And as we look at this, you kind of see a gentle increase up, but note the y-axis. We're really only talking about 1 petagram in total. And so right about the time that our 2010 science paper came out, another paper was published in Nature called Planetary Boundaries. And this was by another group of global change scientists, mostly from Europe, Sweden, Germany, places like that. And they theorized that a lot of the attributes of the functioning Earth system might have some sort of limit, might have some sort of boundary, that if we go over the edge, the system could really crack up. It could break, collapse, really run amok. And this turned out, we couldn't believe it. The politicians listened to it. And so Rockstrom, the lead author, I had lunch with him in Copenhagen in 2014. And I said, did you ever think this would get as hot as it did? He says, I had no idea. The politicians, somehow this concept clicked in their mind that the Earth really is a finite system, and these are attributes of that system: atmospheric aerosols, chemical pollution, climate change, ocean acidification. All the big topics were on this diagram. And they were basically arguing, if we go over a bunch of these limits, this Earth system could actually crack up. And we better start paying attention. So in 2012, I thought, well, I've got a whole global data set of this attribute of the carbon cycle. And so I wrote a paper to Science on might be a planetary boundary also, this global annual plant growth. And it has a lot of relevance when you start thinking through what this attribute could bring to our understanding of the Earth system. It's an integral part of climate stabilization. It tells us whether bioenergy is going to work or not, and I'll return to that. It's absolutely essential for us understanding food security and ultimately global food producing capacity. And it really defines the terrestrial carbon source and sink. So in the last half dozen years, we've looked at all these topics. And I'm going to have to pop through them kind of quick, but I think the graphics are pretty obvious. First, on bioenergy. I read regularly about expectations of future bioenergy. And this is a graph, and these are different papers written by energy economists projecting future bioenergy development. And the units here are exajoules per year. And if you don't know what an exajoule is, well, I don't either. So we'll just use this in a relative sense. It's an energy unit at large scale. The point I want to make is when we looked at our measure of annual plant growth coming from our satellite data set, we only think you can grow about this much bioenergy. And they're expecting this much bioenergy. So we think they're probably a factor of 10 too optimistic in a lot of these estimates of what bioenergy can do for global energy. That's a big difference. Food security, similar sort of thing. This is looking at different regions of the world, and these were computing per capita food production. Let's just look at the top graph as the whole world. It's been going up until the last couple of decades. It rattles around. As they project forward, they expect per capita food production to go down. They don't think we can sustain the food production that we have now. And so this, again, is the kind of thing our data set is an integral part of the analysis. When you get to climate, the terrestrial carbon source sink looks like this. The source, here's the fossil fuels we always hear about. 87% of carbon emissions every year from fossil fuels, but 13% are from deforestation and agricultural burning. Not a trivial amount. Where does it all go? Well, here's the Keeling curve. The part that ends up in the atmosphere and that is now at 410 parts per million, that's about half of the carbon emissions. The other half, the oceans and the terrestrial system are currently taking up. They're helping us a lot. And so the issue for global carbon management is there a way we could get the terrestrial biosphere to take up more carbon and slow down the CO2 increase in the atmosphere? And so our data set is right in the middle of that really critical theoretical question in climate stabilization. And of course, the other half of it is what would happen if the terrestrial biosphere got weaker and started taking up less carbon. Then we'd be in worse trouble quicker. And so these data sets are right in the middle of climate stabilization, bioenergy analysis, of food security analysis. I think this is a look, another look at carbon cycle, and I'm going to go past it because I think we're getting to the end. This is kind of the bottom line looking forward. And this is IPCC model runs. Here we are right here. And this is what I used to call the Dick Cheney curve, but I guess I need to relabel it. Basically, the business as usual if humanity makes no adjustments to energy use. And then this is a number of pathways of slowing carbon emissions down and where we end up at the end of the century in 2100. Now, a lot of people misunderstand this graph and they think this is model error somehow. No, this isn't model error. This is human error. This is humanity deciding what we're going to do. I don't know what we're going to do. At the moment, we're not doing near enough, that's for sure. And so the modeling tries to look at possible futures based on assumptions of what humanity will do in terms of slowing and stopping carbon emissions and fossil fuel use. And the models simply try to represent that fact with all these different scenario runs. And so we really could end up here, 3-4 degrees centigrade higher temperature. Maybe we could end up down here, but there's no evidence to suggest that with current policy and current momentum, shall we say, of humanity. And so this is kind of the look at the future that IPCC tries to do every 5 years is this graph right here. Now, a couple last things on Earth science that are new. One of them, we didn't used to be able to put our Earth science sensors on the space station because that was part of human spaceflight. That was another part of NASA, and they didn't let us play with their toys. But about 5 years ago, they welcomed our sensors on. So now in Earth science, we have, you see a number of sensors on the space station. And this is tremendously valuable because it's basically free. I mean, these little sensors, they go up with an astronaut launch and are bolted on outside, and you don't have to have an entire rocket launch to put a sensor in orbit. So this has been a tremendously good test bed for new sensors that it's really just started. It isn't the best orbit, but we'll take it. It works so well for us. Now, I've read suggestions that they're going to mothball the space station in 2025. And I hope that's not the case, but we'll find out. The other thing I want to mention about how earth science, and particularly the satellites in earth science, are changing so much is when my career started with that big Terra platform that was the size of a bus and weighed thousands of pounds. Nowadays, the new rage are what they call CubeSats, and even drones for just low altitude aircraft. But these CubeSats are, some of them are as small as my fist. There's some company that's launching these little satellites by the hundreds. And they have a completely different philosophy. Instead of one big perfect satellite, they can throw hundreds of them in the air. They're so cheap. They launch them by the dozens. And we're going to have a whole constellation of these CubeSats in the future that you'll be able to look any place on Earth instantaneously at very high resolution, because at any given time there'll be one of these CubeSats right over the top of whatever you want to see. And right now you have to wait till the orbit comes around and get a picture. And the future I really see with these CubeSats is going to be wild. And so these are a couple of things that are, I guess, it occurred to me, it's the kind of thing that forces you into retirement, because it's such a complete flip over the kind of global scale science I did my whole career, and yet that's a major part of the future. So, last slide, the Earth from 1 billion kilometers away, and now we have one even farther away with Voyager. But you sure, when you hang around with the planetary people and they show you these pictures and Earth's just one little dot out there in the middle of nothing, in a way it's kind of frightening. Because, man, there's nothing else except this. And you know, after that movie where, who was it, went to Mars and was growing potatoes and things like that, I had people come up and say, well, couldn't we just go to Mars if things get too bad here? Are you serious? For that amount of money, we could fix things here. And so we're going to be here for forever, and we better take that attitude. So that's the history of NASA Earth Science as told by me. Thank you.
Alrighty, we're going to take some questions from the audience. There's 2 of us. If you could make sure to raise your hand, we'll come around. And yeah, we need the microphone so that MCAT can pick everything up.
No questions, man. This is easy. Oh, heck.
I just saw on that model about planetary boundaries. If I read it correctly, the nitrogen cycle and biodiversity were more crucial than climate change. Can you explain that?
I don't really want to defend that particular part of that scheme. The biodiversity people think we're already losing species on a global scale at an accelerated rate. To me, the bigger issue, being a measurement guy, is we don't really have measurements on a global scale that have any precision of things like biodiversity loss. And so the point I was trying to make there is that this idea that there are limits to the Earth, this planetary boundary paper somehow triggered with the politicians. I can't tell you how many thousands of papers we've written that they never paid any attention to. And somehow they paid attention to that. To this day, I read political and policy documents referring to planetary boundary framing. And so if you take it too literally and ask too detailed a question like you're doing, it can get a little shaky. But if you think of it as a framing that helps somebody with a non-science background realize that we really could overrun this planet in multiple ways, and we better start paying attention. That's really the punchline of that planetary boundary argument. I mean, they didn't have any carbon cycle variable at all. That's why I wrote my 2012 paper. So when you start looking at details of that, there's easy to poke holes. Yeah.
Thank you. I have three things. One thing is thank you for making this science understandable to me. I really, really appreciate that, and I hope that you and people like you are going all over telling your experience. And
No, I'm retired.
I know, but
This is
you're
about
out
my
here.
last talk, actually.
Oh, thank you. Thank you very much. And then I saw in the paper, kind of in the newspaper the other day, that there was a satellite shot showing the increase in forestation in
In China and India.
Yeah, yeah.
Raman Namani, your distinguished alumni, was an author of that paper.
Okay.
And they were using the satellite you just heard about.
Okay, cool.
Yeah, and that was interesting to see that China and India, with their huge population densities, are measurably greening. And you know, satellites don't lie. There's no politics in the spectral signal. And so when it comes out like that China and India are greening, I believe it. So that was a cool paper.
My question is, what do you see, I guess besides the obvious being funding, as the greatest threat to research in this area?
I don't actually see a threat to the research. I see a threat to anybody listening to it. Our research is doing just fine. We're actually reasonably well funded. And of course, I'm not writing grants anymore, so I can say anything. But the research is going fine. It's the fact that none of the policymakers seem to sink in the message that the research tells them.
Did you vote for Reagan and Bush?
If I'd known Reagan was going to jumpstart my career, I maybe should have. Excuse me. I thought the mic went somewhere. Okay.
Yeah, just going off that last comment about the paper, isn't it the case that, yes, it was greening, but some of the greening of those countries was mostly agriculture, and some of it was, I guess, rice paddies in those areas? And
It beats having a shopping mall.
right, but it might have alternative effects on the climate when we're talking about rice paddies and methane emissions.
Mm-hmm.
So when we're I was wondering what your take was on greening versus how that relates to the global climate.
Well, this is the kind of oh man, let's hope my throat doesn't give up now. This is the kind of analysis we do on every square kilometer. From the boreal forest all the way to India and the Amazon and everywhere. And when you see a change in that land cover and you perceive a change in the photosynthetic production, it can go either way. It can be getting better, it can be getting worse. So it's hard to generalize with any given spot. Take, for example, the rice paddies. If you're a biodiversity person, you'd maybe say, well, the rice paddies I'm not so excited about. But if you're a food security person, you might be all for them. And so our first job as global scientists is simply to measure accurately what's happening. The second step is then to determine if that's the best use for that land or trajectory for that region. But, and that gets into socioeconomic issues that our measurements aren't about. We're just trying to say, here's what's happening. And everywhere is different. Some places you want to be growing food, some places you want to have wilderness, so there's no easy answer that you can use everywhere.
One question, you're retiring or have retired. Is there somebody replacing you here at the university?
No.
How do we get them here?
Now, I still have my NASA grant going, and so I'm still funded to continue this work. So in the immediate sense, this work is not ending, but they did not refill my position.
Any more questions?
This is a lot easier than I was at the Jet Propulsion Lab last week, and I got pounded pretty bad there.
Okay, well,
Okay.
thank you to Dr. Stevens.